The red planet is hiding astonishing secrets in plain sight. For decades, our robotic explorers have traversed its dusty plains and scanned its ancient cliffs, sending back a treasure trove of images that often leave even the experts speechless. This is a journey through 30 of the strangest, most baffling things ever found on Mars. By the end, you will see our neighboring world not as a dead rock, but as a dynamic puzzle box of geological wonders and lingering mysteries. We will encounter formations that look sculpted by tools, substances that hint at hidden water, and atmospheric events that defy all explanation. What could explain a perfect doorway carved into a cliff, or seasonal gas plumes that whisper of possible life? Which of these Martian mysteries makes you question everything you thought you knew about that rusty world next door? Our journey begins with a single image that ignited a global obsession. In July of 1976, NASA Viking 1 orbiter was mapping a region called Cydonia when its camera captured something astonishing. There, etched into the Martian landscape, was what appeared to be a colossal human face. It was over a mile wide with distinct eyes, a nose, and a mouth, seemingly staring solemnly up at the cosmos. The public reaction was immediate and electric. Newspapers ran sensational headlines and a wave of speculation surged. Was this proof of a lost Martian civilization, a monument left by ancient beings for us to find? The idea captured imaginations, suggesting that Mars was not just a planet but a tomb for a forgotten history. This single frame fueled decades of books, documentaries, and elaborate theories about intelligent builders. Then, decades later, came the clarity. Missions like Mars Global Surveyor arrived with far more powerful cameras. When they turned their gaze back to Cydonia in the late 1990s and beyond, they revealed the truth in stunning detail. The face was gone. In its place was an ordinary, if strikingly shaped mesa, a flat-topped hill carved by millions of years of wind erosion. The haunting visage had been a perfect illusion, a combination of low-resolution, dramatic sunlight casting deep shadows and the angle of the shot. This is the textbook example of a powerful psychological phenomenon called pareidolia, our brain's hardwired desire to find meaningful patterns, especially faces, in random shapes. We see the man in the moon, animals in clouds, and for a time, a giant face on Mars. While the mystery was solved, its legacy is undeniable. That one grainy photo did more than spark a myth. It fundamentally changed how we look at Mars. It taught scientists the critical importance of high-resolution follow-up, and it taught the public to question first impressions. Most importantly, it opened the door. If our eyes could be so fooled by a simple hill, what other genuine wonders might be hiding in plain sight, waiting for a closer look? The ghostly face of Cydonia was a powerful illusion, but not every Martian mystery dissolves under sharper scrutiny. Some become more profound. After the disappointment of the face, many wondered if Mars would ever yield a tangible, physical clue to its past. Then, in 2004, a little rover named Opportunity rolled to a stop in a place called Meridiani Planum, and its cameras revealed a landscape that looked utterly alien yet strangely familiar. The ground was littered as far as the eye could see with countless tiny, perfect spheres. They were scattered across the soil like marbles spilled from a giant's pocket, or beads of iron sprinkled over the rust-colored sand. Scientists instantly gave them a whimsical nickname, the Blueberries of Mars. In false color images processed to highlight mineral differences, they appeared as deep blue dots against the red terrain, hence the name. But these were no simple stones. Analysis by the rover's instruments revealed their true nature. They were concretions, solid balls of the mineral hematite, a form of iron oxide that often forms in the presence of liquid water. This was not a trick of light and shadow. This was physical, undeniable evidence written in stone, or rather, in millions of tiny ironstones. The process that created them is one we know well from Earth. Picture groundwater rich in dissolved minerals like iron, slowly seeping through porous rock beneath an ancient Martian surface. Under the right chemical conditions, the iron begins to precipitate out of the water, crystallizing around a central nucleus, a tiny grain of sand, perhaps. Layer by microscopic layer, the sphere grows like a pearl forming in an oyster until the surrounding rock erodes away, leaving the hardy concretion behind to roll freely across the ground. The sheer abundance of these blueberries at Meridiani Planum told a revolutionary story. It meant that liquid water, and not just a fleeting puddle but substantial groundwater, had persisted in that location for a very, very long time. This was the first concrete proof, one could literally pick it up with a robotic arm, that Mars once had a wetter, potentially habitable past. The blueberries transformed our understanding from speculative to certain. The planet next door was not always the dry, frozen desert we see today. It had the ingredients, the water, and the time necessary for the chemistry of life to perhaps begin. While they are not fossils, these tiny iron spheres are fossils of an environment, silent witnesses to an era when Mars whispered with the flow of water. The blueberries were a quiet testament to ancient water, but Mars had a far more dramatic trick up its sleeve a decade later. In late 2013, NASA, a veteran Opportunity rover, was examining a familiar patch of ground at a location called Murray Ridge. Mission controllers sent the usual command for the rover to take a panoramic image, a routine survey of its surroundings. When the data arrived back on Earth, a scientist named Steve Squires was reviewing the photos. His eye caught something impossible. Right there in the foreground, where just 12 Martian days before there had been only empty soil, now sat a rock. It was about the size of a donut with a startling white rim and a deep, dark red center. The team was floored. Nothing like it had been seen in the rover's decade of travel. They nicknamed it Pinnacle Island, but everyone quickly started calling it the Jelly Donut Rock. How did it get there? The initial theories ranged from the spectacular to the extraordinary. Could it be a meteorite that had just fallen from the sky, landing with improbable precision right in front of the rover's cameras? Some even dared to wonder if it was a sign of something biological, a fungal-like growth that had sprouted from the Martian soil. The mystery captivated the public, a sudden, tangible puzzle delivered from another world. The answer, uncovered after careful analysis of the rover's tracks and earlier imagery, was both mundane and brilliant. Opportunity had not been stationary. In the days before the rock appeared, the rover had performed a small maneuver, turning in place. One of its 6 wheels had clipped a partially buried rock just a few feet away. The motion acted like a boot kicking a stone, flipping the rock end over end until it landed squarely in the new, empty spot. The jelly donut was not a new arrival from space or a living thing. It was an old rock that had simply been turned over. The white rim was the underside, likely coated with different minerals or dust that had been protected from the surface winds and oxidation. This incident was a profound lesson. It revealed the Martian surface as an active, dynamic place, where even a slow-moving robot could dramatically alter the landscape and reveal hidden secrets. The Jelly Donut Rock underscored the immense challenge and serendipity of remote exploration. Scientists are not just passive observers on Mars, they are active participants, sometimes uncovering mysteries not because of careful planning, but because of a lucky bump from a robotic tire. The Jelly Donut Rock was a lesson in perspective, but sometimes Mars presents a mystery so intricate it feels almost crafted. During a routine survey in February of 2022, the Curiosity rover's microscopic camera, known as the Mars Hand Lens Imager, captured something extraordinary nestled within a craggy rock named the Gale Crater. It was a tiny, delicate protrusion no larger than a coin, yet its form was stunningly complex. To the human eye, it looked exactly like a piece of coral, a miniature seashell, or a fragile flower frozen in stone. The internet, of course, erupted. Was this a fossil, the preserved remnant of some ancient Martian marine life, forever etched into the bedrock of a long-dead sea? The image was so evocative it was hard to believe it was just a rock. Scientists, however, quickly recognized this beautiful object for what it almost certainly is, a diagenetic feature. That's a geological term for a structure formed long after the original rock was laid down. Here is how it likely happened. Billions of years ago, when this part of Gale crater was wet, mineral-rich water seeped through tiny fractures and pores in the sediment. Over immense stretches of time, those minerals, possibly sulfates or other salts, slowly precipitated out of the water, crystallizing and filling the voids. This created a small, hard lump of mineral that was actually more resistant to erosion than the surrounding, softer rock. Then the wind took over. Eons of relentless Martian sandblasting wore away the softer material, leaving behind the harder, more durable mineral formation in exquisite three-dimensional relief. What we are seeing is not the remains of a living thing, but a natural mold, a ghostly imprint of where water once flowed. These tiny, flower-like features are among the most valuable clues a geologist can find. They are not just pretty curiosities, they are direct physical evidence of the chemical interactions between liquid water and rock. They tell us not only that water was present, but also about its composition, its pH, and how long it persisted in the environment. This Martian flower, then, is a bloom of mineralogy, a silent but eloquent witness to the planet's dynamic and watery youth. It reminds us that the most profound stories are often written in the smallest details, etched by chemistry and time. That delicate mineral flower reveals how water shaped Mars, but another curiosity image seemed to show something shaped by intelligence. In May of 2022, the Rover's massed camera captured a photograph that went viral across the globe. There, set into the layered rock of a cliff face, was what appeared to be a perfect rectangular doorway. It looked precisely carved, with a dark interior beckoning from within the stone, an entrance straight out of a science fiction novel. The mind raced with possibilities, a hidden tomb, a secret shelter, a passage to an underworld carved by ancient Martians. The allure was primal. We are a species that builds entrances from the front doors of our homes to the grand gates of our cities, so our eyes are irresistibly drawn to that familiar shape on an alien landscape. The reality, however, is a masterclass in scale and geology. What appears as a grand, person-sized portal is, in truth, only a few inches tall. Our rover companion, Curiosity, provides the sense of scale, its tracks and the surrounding boulders shrinking the illusion down to size. This tiny crevice is not an architectural feat, but a geological one. The cliff is made of sedimentary rock deposited in layers over eons. Under immense stress, perhaps from the weight of overlying material or from distant Mars quarks, the bedrock naturally fractures. These fractures often follow straight lines, creating clean, geometric cracks. Then, the relentless Martian wind takes over. Sandblasting for millions of years can erode material along these fracture lines, widening a crack and undercutting the rock above it, often resulting in surprisingly sharp, rectangular alcoves. This combination of natural stress fracturing and persistent wind erosion is the planet's sculptor, not some lost civilization. This Martian doorway is a powerful reminder of two fundamental truths. First, the sheer scale of planetary geology can utterly deceive us, making a crack in a rock look like a monumental gateway. And second, our pattern-seeking brains are a double-edged sword. They help us make sense of a chaotic world, but on Mars, they often see the familiar in the profoundly alien. The true wonder is not that someone built a door, but that the natural forces of Mars can create a formation so uncannily perfect that it makes the entire world question what is possible. The Martian doorway is a trick of fractured rock, but some formations on the red planet are genuine echoes of a lost landscape. Scattered across vast plains, often in hauntingly repetitive patterns, are fields of strange, crescent-shaped ridges. They look like the bleached ribs of some colossal creature or the fossilized footprints of a giant. These are the ghost dunes of Mars. They are not dunes at all, but they're perfect inverted impressions, solid stone memories of where immense mountains of sand once stood. The story of a ghost dune begins in an ancient, windy Mars. Picture towering sand dunes hundreds of feet tall, marching slowly across a valley under a relentless, rusty wind. Then a dramatic change. Perhaps a volcanic eruption blankets the region in ash, or a flood of water-borne sediment slowly rises, quietly burying these massive dunes in a thick, protective layer of silt and dust. Over millions of years, that blanket of sediment, under its own immense weight, hardens into solid rock. It becomes a tomb of stone. Meanwhile, something remarkable is happening inside the buried dunes themselves. Mineral-rich water begins to seep down from the surface, percolating through the buried sand. This water acts as a kind of glue, cementing the sand grains together, turning the very heart of the dune into a slab of sandstone that is actually harder than the material that buried it. Then the great reveal. The wind returns, but this time as an eraser. Over more eons, it scours away the softer rock that once covered the dunes, wearing it down and carrying it off grain by grain. But the hardened dune core, that cemented sandstone, resists. As the landscape is stripped lower and lower, these durable forms are left standing in relief. What was once a valley between dunes becomes a high ridge, and what was the peak of the dune becomes a protected hollow. The entire topography is flipped like a plaster cast of a footprint. Today, we see not the dune, but the empty space it once occupied, now filled with hardened stone. These ghost dunes are far more than just geological curiosities. Their perfect crescent shapes are frozen compasses, pointing directly to the direction of the prevailing winds that shaped them billions of years ago. Even more tantalizing is what they might hide. The protected spaces within and between the layers of these ancient dunes could have been ideal micro-environments, shielded from harsh surface radiation and extreme temperature swings. If ancient microbial life ever existed on Mars, these stone ghosts might be the perfect traps, having captured and preserved organic material in their sandy pores for us to one day discover. They stand as silent sentinels, not just marking where the wind once blew, but potentially safeguarding the faintest whispers of a biological past. Ghost dunes hold the shape of ancient winds, but another Martian mystery breathes with a modern rhythm, a gas that appears and vanishes with the seasons. Methane on Mars is not just a scientific curiosity, it is a pulsating enigma that cuts straight to the core of our greatest question. Both Earth-based observatories and the Curiosity rover, sniffing the air inside Gale Crater, have confirmed something startling. Tiny, intermittent plumes of methane gas seep into the thin Martian atmosphere, and they do so in a pattern that seems to follow the planet's own calendar, spiking predictably in the local summer months. On our own world, methane is a signature of life. The vast majority of it in our air is produced by biological processes, from the digestive tracts of cattle to the subtle workings of microbes deep underground or beneath the sea. It can also be made by purely geological means, like the interaction of hot water with certain kinds of rock in a process called serpentinization. So when we detect methane on Mars, the implication is electric. Could these seasonal whispers be the metabolic exhaust of a hidden biosphere, of Martian microorganisms clinging to existence in damp pockets beneath the frozen soil, releasing their gas as the ground warms? It is a breathtaking possibility, yet the scientific community is fiercely divided because non-biological explanations are equally plausible. The same geothermal chemistry that occurs on Earth could be at work deep within Mars. Water, perhaps still liquid in insulated aquifers, could be reacting with olivine-rich rock, producing methane as a byproduct that then slowly percolates to the surface. Alternatively, the methane might not be fresh at all. It could be ancient gas produced billions of years ago and trapped in ice like structures called clathrates, which slowly crack open and release their stored contents when warmed by the summer sun. Each new data point from curiosity deepens the mystery rather than solves it. The rover has even detected sudden, dramatic spikes of methane that appear and dissipate within a single Martian day, suggesting a local, elusive source. This is not a distant signal, it is a neighborhood event. Solving the methane riddle has become one of the highest priorities in planetary science because the answer points to one of two profound truths. Either Mars is geologically more active and aqueous than we ever dreamed, or it is, right now, a living world. Every whiff of that simple gas is a clue written on the wind, a single word in a sentence we are desperately trying to read. Methane whispers on the wind, but some Martian mysteries are written boldly across the hillsides for all to see. On sun-warmed slopes across the southern hemisphere, strange dark tendrils reach down from ridges and crater rims. They appear each spring, lengthening like Inkai fingers through the summer, only to fade and vanish when the cold returns. Scientists call them recurring slope lineae, or RSL, and for a time they represented the hottest, most promising clue to modern liquid water on Mars. The evidence seemed compelling. These streaks followed the warmest ground, appearing when surface temperatures were most favorable for liquid. Their behavior mirrored what we would expect from a seep of salty water or brine. Salt lowers the freezing point of water dramatically, allowing it to remain liquid in the frigid Martian cold. The hypothesis was explosive. It suggested that even today, Mars might not be entirely dead, that just inches below the surface, in the right places and seasons, liquid water could still trickle, offering a potential refuge for any surviving microbial life. This idea wasn't just exciting, it was paradigm-shifting. If RSL were truly wet, they would be the most accessible potential habitats on the planet, and also a profound contamination risk for our rovers. Planetary protection protocols designed to prevent Earth microbes from hitchhiking to Mars would demand we avoid these areas entirely, lest we spoil our own search for life. But science thrives on new data, and the story of the dark streaks took a dramatic turn. As orbital instruments like the Mars Reconnaissance Orbiter studied them with even greater precision, a different picture emerged. Detailed spectral analysis looking for the chemical fingerprints of hydrated salts that will be left behind by evaporating brine came up largely empty. The streaks showed no consistent signature of water. Then, researchers began to model another possibility: dry granular flow. Imagine a steep slope of fine, dark sand and dust. In the Martian spring, frozen carbon dioxide frost or dry ice that has accumulated on the slope during winter begins to sublimate, turning directly from solid to gas. This process can destabilize the overlying sand, triggering small avalanches. The dark material tumbles down, revealing a fresh, darker layer beneath that contrasts sharply with the brighter, dust-covered surroundings. As the season progresses and the sun heats the dark streak, it creates a small thermal anomaly, a self-perpetuating cycle where the warm streak encourages further sliding of nearby grains. This dry process can perfectly mimic the appearance and seasonal timing of a liquid flow without a single drop of water being involved. The debate is far more than academic. It cuts to the heart of two critical issues. First, it defines our understanding of Mars as a modern world. Are we looking at a planet where liquid water still occasionally breaches the surface, or one where all surface activity is driven by dry, mechanical processes and the ghostly phase changes of carbon dioxide? Second, and more practically, it dictates the future of exploration. If RSL are wet, they are strictly off-limits for our current, not fully sterilized robots. If they are dry, they become fascinating geological targets, not biological ones. This unresolved tension makes every new observation of these dark streaks a high-stakes investigation. They remain one of Mars's most visible and perplexing puzzles. a reminder that even the most obvious clues can point in two completely different directions, each leading to a radically different vision of the world next door. While the dark streaks debate the presence of water today, other Martian features reveal its icy history locked just beneath the surface. From high above, the Mars Reconnaissance Orbiter has captured landscapes that look less like geology and more like the hide of a colossal, slumbering dragon. Vast plains are tiled with intricate, interlocking patterns, a mosaic of sharp ridges and deep troughs that resemble gigantic, overlapping scales. This is not the work of some mythical beast, but of one of the most powerful forces in a cold climate, the simple act of water freezing and thawing over cosmic timescales. Scientists call this polygonally patterned ground, and it is a telltale signature of subsurface ice. The process is slow, relentless, and beautifully logical. Picture the Martian soil or regolith permeated with water ice. As temperatures drop, that ice expands, exerting immense pressure on the surrounding soil and rock. This creates stress fields that naturally organize into a network of fractures, much like the way mud cracks as it dries, but on a vastly larger scale. Over countless cycles, season after season, millennium after millennium, this repeated expansion and contraction along the fracture lines pushes up ridges of soil and sorts larger stones to the edges of each polygon. What emerges from this endless, gentle churning is a sprawling, geometric artwork etched across the planet's polar and mid-latitude regions. These dragon scales are far more than a visual oddity, they are a global map to a buried treasure. By studying their size, shape, and distribution, planetary scientists can literally chart where and how close to the surface this valuable water ice lies. For future human explorers, this information is not just academic, it is absolutely critical. Water is the key to survival on Mars, not just for drinking, but for growing food and producing breathable oxygen. More importantly, it can be split into hydrogen and oxygen, the fundamental components of rocket fuel. Finding accessible ice means a mission could potentially live off the land, turning Martian resources into the propellant needed for the long journey home. These polygonal patterns, therefore, are more than a frozen curiosity. They are the first draft of a blueprint for human expansion, a natural signpost pointing to the very substance that could one day fuel our first interplanetary outpost. The dragon scales are a frozen map to buried water, but at the planet's southern pole, the ice itself comes alive in a truly alien spectacle. From high orbit, the springtime landscape of the Martian South Polar Cap transforms into a scene of eerie, crawling life. Vast fields are etched with dark, sprawling patterns that look uncannily like gigantic spiders, with countless thin, branching legs radiating from a central body. These are not living creatures, of course, but they are the scars of a violent and uniquely Martian spring ritual, a process that exists nowhere else in our solar system. The drama begins in the profound cold of the polar winter, when a layer of translucent carbon dioxide ice, or dry ice, forms a solid pane over the darker, dusty ground below. When the sun returns in spring, its rays penetrate this clear surface ice like a lens, warming the dark soil beneath. This heat does not melt the dry ice above. Instead, it triggers a direct phase change from solid to gas, a process called sublimation. The carbon dioxide at the base of the ice layer turns into gas, but it is trapped, sealed beneath the frozen slab. Pressure builds relentlessly in the pocket below, searching for any weakness. Finally, the pent-up gas finds a fissure or a thin spot in the overlying ice. It erupts upward in a jet-like geyser, bursting through with enough force to carry dark basal dust and sand high into the thin air. This explosive venting carves a narrow channel through the ice as it escapes. Over countless Martian springs, the same spots reactivate. Each eruption widens and deepens the channels, and the escaping gas, laden with dark material, fans out and falls back to the surface, staining the ice in intricate dendritic patterns. What we see from space as a spider's leg is actually a deep, eroded trough, and its central body is a dark, stained pit where the jet finally breached the surface. This entire cycle, from trapped sunlight to explosive geyser, is a purely Martian phenomenon. Earth has no widespread deposits of dry ice on its surface to sublimate in this way. These spiders are therefore more than just a strange sight. They are a testament to the exotic nature of Martian geology, where the very atmosphere freezes solid and then escapes in violent, artistic bursts. They remind us that the processes shaping other worlds can be fundamentally different from our own, turning a simple change of season into a landscape of apparent crawling life. The spiders are a testament to the power of sublimation, but sometimes the Martian landscape seems to sculpt figures that walk. During its exploration of the Columbia Hills, the Spirit rover captured an image that, for a brief moment, sent a different kind of chill through the public imagination. There, perched on a ridge against the hazy sky, was a formation that to many eyes looked unmistakably like a crude humanoid figure, a stick-figure man taking a solitary stroll across the rust-colored hills. The silhouette seemed to have a head, shoulders, and legs caught mid-stride, a lonely wanderer forever frozen on an alien plane. It was an instant classic of Martian pareidolia, our brain's irresistible urge to see the familiar in the utterly foreign. A closer, scientific look at the image dissolves the mystery with fascinating clarity. The figure is not a single entity but a clever juxtaposition of several small rocks at different distances from the camera. The head is a rounded stone perhaps only a few inches tall, sitting atop a larger, sloping boulder that forms the shoulders and torso. The legs are another separate rock formation in the background, perfectly aligned by perspective to complete the illusion. The low-angle sunlight of the Martian afternoon casts long, dramatic shadows that blend these distinct elements into a cohesive, walking shape. It is a perfect storm of coincidence, scale, and lighting, a random arrangement that our pattern recognition software, the human brain, is hardwired to interpret as a living form. This stick figure, like the face of Cydonia before it, is not evidence of Martian art or life, but evidence of how we see. On a world where every stone and shadow is alien, our minds desperately seek anchors, something recognizable to latch onto. This cognitive shortcut is vital on Earth, helping us spot a predator in the bushes, but on Mars, it leads us astray, painting pictures where there is only geology. The true lesson of the walking rock is not about what is on Mars, but about how we look at it. It underscores why context is everything in exploration. A single intriguing image is just a pixel, a solitary clue. Science demands the panorama, the chemical analysis, the repeated observation from different angles. It requires us to quiet the part of our brain that shouts "figure," and let the instruments and the evidence tell the slower, more complex, and often more wondrous story of a world shaped by wind, time, and chemistry, not by hands. Our brains may see walking figures, but our rovers are equipped to see chemistry. In November of 2018, Curiosity's massed camera spotted something that gleamed like a misplaced piece of jewelry on the dull, gray bedrock of the Vera Rubin Ridge. It was a small, bright sliver, no larger than a pill, standing out with a brilliant, metallic luster against its surroundings. The mission team quickly nicknamed it Little Colonsay, and its unusual shine immediately sparked a compelling hypothesis. Could this be a fragment of a meteorite, a piece of iron-nickel from the asteroid belt that had survived its fiery plunge through the thin Martian atmosphere to land at the rover's feet? Mars is littered with such metallic visitors, and finding one would be a valuable sample of material from deep space. But on Mars, assumptions are invitations for investigation. The rover was commanded to perform a precise and dramatic analysis. It aimed its ChemCam instrument at the tiny speck. ChemCam fires a powerful laser, heating a pinprick spot on a target to a searing 10,000 degrees Celsius, creating a brief, glowing puff of vaporized plasma. By analyzing the light from that miniature star, scientists can determine the object's elemental composition. the team zapped little Colonsay, eagerly awaiting the data that would confirm its extraterrestrial metallic origin. The results, however, told a different story. The shiny fleck was not a meteorite. Its chemical signature pointed not to iron and nickel, but to something more mundane, yet still fascinating, a concentration of naturally occurring high-reflectance minerals. It was most likely a piece of silica or a similar mineral that had formed under special conditions, giving it a glassy, mirror-like finish that caught the sunlight perfectly. This tiny episode is a perfect capsule of the scientific method in action on another world. Observe an anomaly, form a hypothesis, test it with a direct experiment, and let the data dictate the conclusion. Little Colonsay was not a space treasure, but the process of discovering that fact was itself a treasure of methodology. It reminds us that the true discovery is not always the answer we hope for, but the rigorous path we take to find it, a path illuminated by the flash of a laser on a distant ridge. Curiosity's laser revealed a shiny mineral, but its cameras have captured far grander and more haunting sculptures. As the rover has climbed the lower slopes of Mount Sharp, the central peak of Gale Crater, it has entered a landscape of silent, towering giants. These are the hoodoos of Mars, slender spires of rock that rise like petrified sentinels from the dusty floor, their tops crowned with dark, durable caps that look like stone mushrooms or weathered hats. They are eerily familiar to anyone who has seen the breathtaking vistas of Bryce Canyon on Earth, where similar formations create a forest of stone. The process that builds them is a universal sculptor, a patient battle between hard and soft rock. It begins with layered deposits, sediments laid down over eons in an ancient Martian lake or by relentless winds. These layers are not uniform. Some are soft clay or loose sandstone, while others are cemented into much harder slabs by mineral-rich water. When the relentless Martian wind, carrying its abrasive dust, sweeps across this landscape, it acts like a cosmic sandblaster. It easily scours away the softer material, but it meets fierce resistance when it hits a layer of that hardened cap rock. This resistant layer becomes a natural umbrella, shielding the softer pillar directly beneath it from the full force of erosion. Over millions of years, the unprotected surroundings are worn down, while the protected column stands tall, becoming more and more isolated, until all that remains is a slender spire upholding its sturdy cap. These Martian hoodoos are more than just beautiful oddities. They are history books written in stone. Their very structure, with distinct layers of hard and soft rock, records a dramatic planetary story. The alternating layers suggest that Gale Crater did not have a single, stable environment. Instead, it oscillated wildly between wet and dry eras. One layer might be lakebed mud, hardened by minerals from standing water, perfect for preserving the chemical ingredients of life. The layer above it could be a cross-bedded sandstone deposited by powerful desert winds, telling of a time when the lake had vanished and drought ruled. Each hoodoo is a vertical timeline, a core sample of climate change on a planetary scale, showing us that Mars didn't just die, it experienced dramatic, cyclic transformations. By studying the composition of each cap and each protected layer, scientists can read the sequence of events that built Mount Sharp, deciphering chapters of a history that spans billions of years, from deep water to blowing sand, all frozen in these lonely, enduring pillars. Hoodoos stand as monuments to slow erosion, but some Martian phenomena explode into view with shocking speed. In March of 2012, a group of dedicated amateur astronomers on Earth trained their telescopes on the red planet's limb, the thin line of its atmosphere backlit by the sun. What they witnessed defied all expectations. A brilliant, diffuse plume erupted over the planet's southern hemisphere, a colossal tower of brightness reaching an estimated 250 kilometers above the surface. For about 10 days, this impossible formation was visible, a stark anomaly against the blackness of space. Then, just as mysteriously, it vanished. 3 years later, in 2015, it happened again. This time, the plume was captured by the powerful Hubble Space Telescope, confirming the earlier sighting was no illusion. These were not subtle features, they were atmospheric mountains towering over the Martian landscape at altitudes where the atmosphere is vanishingly thin, more than twice as high as any cloud or weather phenomenon ever recorded. The scale was staggering. If such a plume occurred on Earth, it would reach from the ground into the upper layers of our ionosphere. So what could possibly create such a towering, transient structure in Mars's wispy air? Scientists scrambled for explanations, each theory pushing the limits of our understanding. One leading idea points to colossal clouds, but of an extraordinary kind. On Mars, clouds are typically made of water ice crystals and form only up to about 100 kilometers. Could these plumes be immense concentrations of such crystals, reflecting sunlight with exceptional brilliance? Perhaps, but the energy required to loft water vapor that high is immense. Another possibility involves carbon dioxide. In the cold Martian upper atmosphere, CO2 could theoretically freeze into tiny ice crystals, creating reflective clouds far higher than water could ever reach. Yet the dynamics of forming such a dense, localized cloud remain poorly understood. A more exotic theory suggests an auroral phenomenon. On Earth, energetic particles from the Sun collide with our magnetic field, creating the shimmering curtains of the northern lights. Mars lacks a global magnetic field, but it does have localized, fossilized magnetic fields locked in its crust. Could a massive solar storm have interacted with one of these magnetic anomalies, causing a brilliant, concentrated aurora that glowed across thousands of kilometers? This could explain the plume's brightness and high altitude, but not necessarily its distinct cloud-like shape. The frustrating and thrilling truth is that a decade later, these enormous plumes remain officially unexplained. They were unpredictable, short-lived events that our orbiting spacecraft did not have the right instruments or vantage points to analyze in detail as they happened. They serve as a humbling and electrifying reminder. For all our rovers and orbiters, Mars is still a world of immense scale and fleeting moments. Its thin atmosphere, which we often dismiss as a near vacuum, is capable of producing displays of such magnitude that they are visible from Earth, yet so elusive that their fundamental nature escapes us. These mysterious plumes are a signal from a dynamic planet, a proof that some of its greatest wonders are not etched in stone, but written on the wind, visible only to those watching at precisely the right moment. The colossal plumes remind us that Mars is a world of grand, fleeting spectacles, but sometimes its smallest details capture our imagination with equal force. A few years ago, a routine image from Curiosity's masked camera became a global sensation. There, sitting on a dusty ledge, was what appeared to be a perfectly formed spoon, its bowl and long handle clear against the sky, even casting a slender shadow that made it look as if it were floating in midair. The internet delighted in the absurdity, a lone piece of cutlery waiting patiently on another planet. The reality, while less whimsical, is a stunning demonstration of nature's patient artistry. This is not a lost artifact, but a masterclass in a process called differential erosion. The Martian spoon began its life as part of a larger rock formation, composed of layers with different hardness. Imagine a slab where a thin, durable layer of volcanic rock or cemented minerals sits atop a much softer layer of clay or loose sediment. For eons, the relentless, sand-blasting wind scours the landscape. It attacks the softer material with far greater efficiency, slowly undercutting it grain by grain. The harder, more resistant cap rock erodes at a glacial pace. Over thousands, perhaps millions of years, the wind acts as a sculptor with infinite patience, carving away everything that isn't the spoon. What remains is that slender fin of hard rock, precariously balanced on its dwindling pedestal of softer material. The bowl of the spoon is simply a section where the fin has been sculpted into a concave shape, and the long handle is the thinning extension that hasn't yet snapped off. We see this same beautiful process in deserts on Earth, in the delicate arches and balanced rocks of places like Utah or the Sahara. On Mars, where there is no rain or vegetation to accelerate erosion, the wind works alone with a purity and patience that creates these impossibly fragile forms. The floating spoon is therefore a monument to time and atmosphere. It is a snapshot of a geological moment, a fragile structure that may, with the next strong gust or the subtle tremor of a Mosquak, finally collapse into a pile of ordinary rubble. Its existence is a testament to the serene, slow-motion violence that shapes the red planet, turning solid rock into fleeting illusions of familiarity. That fragile spoon is a testament to wine's patient carving, but other Martian treasures are forged in an instant of apocalyptic fire. Orbiting spacecraft, equipped with instruments that see more than just visible light, have mapped vast fields of impact craters with a strange and telling secret. Their floors and ejector blankets do not reflect light like ordinary rock. Instead, they possess a distinctive spectral signature that points to something unexpected: glass. Not the manufactured kind, but natural glass forged in the most violent workshop imaginable, the heart of a meteorite impact. When a space rock slams into a planet at tens of thousands of miles per hour, it delivers energy comparable to a nuclear detonation. The target rock at ground zero isn't just pulverized, it is instantly vaporized and melted into a superheated soup of molten minerals. This liquid rock then flies outward in a fiery spray, cooling so rapidly in the thin, cold Martian air that its atoms cannot arrange themselves into an orderly crystalline structure. They freeze in place, disordered, creating a solid that is neither rock nor crystal but glass. This impact glass can form in vast sheets, in spattered droplets, or in delicate filaments known as tektites, which we also find scattered across certain regions of Earth. On Mars, however, this glass is more than a geological curiosity. It is a potential time capsule. Scientists have realized that the searing melt from an impact doesn't just vaporize everything, it can also encapsulate it. Imagine the moment of collision. The meteorite strikes a patch of ground that may have been rich with clay sediments from an ancient lake, or even contain traces of organic material. The explosive melt scoops up that material, enveloping it within the forming glass. As the glass chills in milliseconds, it seals whatever was caught inside in a pristine, airtight tomb, protecting it from the ravages of radiation, oxidation, and billions of years of erosion. This makes these glittering impact sites perhaps the most promising hunting grounds on Mars for signs of ancient life. If organic molecules or even microscopic biosignatures existed in that pre-impact soil, they could be preserved in that glass with a fidelity that rivals our best laboratories on Earth. We have seen this preservation power in impact glasses right here on our own planet, where scientists have found ancient plant material locked inside. So while the impact itself is an agent of utter destruction, it also creates these extraordinary natural vaults. A rover or future astronaut visiting one of these glassy craters might not be looking at a scar of death, but at a museum, a glittering preserve where the chemistry of a lost, wet Mars is frozen in time, waiting for us to crack it open. Impact glass preserves the echoes of ancient cataclysms, but on the surface today, the wind is the artist. As our rovers traverse this open-air gallery, they encounter sculptures that seem deliberately placed. One of the most striking is a formation nicknamed the Bishop. Photographed by curiosity, it stands alone on a pediment, a slender column with a wide, flat top that bears an uncanny resemblance to a chess piece, specifically a bishop poised for a game on a planetary scale. It is not alone. The Martian landscape is dotted with these oddities, rocks that look like floating fins, perfectly balanced eggs, or even abstract modern art. Each one feels placed, yet each is a masterpiece of natural Aeolian sculpture. The primary tool is wind abrasion. Mars has a thin atmosphere, only about 1% the density of Earth's, but what it lacks in strength it makes up for in persistence. For billions of years, this whisper-thin wind has carried fine, abrasive dust. It does not blow rocks over, it slowly sandpapers them. The process is exquisitely selective. Softer minerals are scoured away grain by grain, while harder nodules or layers resist. This differential erosion can sculpt a rock from all sides, rounding it into a sphere, or, if the wind is consistently channeled from one direction, carve it into a streamlined, aerodynamic shape called a ventifact. The bishop's distinctive cap likely formed because the top layer was a harder, more cemented slab that protected the softer stem beneath from the full force of the wind-blown sand. But wind is not the only sculptor. Chemical weathering plays a subtle, complementary role. The Martian surface is not inert, it interacts with the tenuous atmosphere. Trace amounts of water vapor can facilitate chemical reactions on rock surfaces, weakening certain minerals. This chemical pre-softening makes the material more susceptible to the physical scouring that follows. The combination of these forces over eons can create impossibly delicate forms. A rock may be undercut so severely it appears to float above the ground, balanced on a tiny point of contact. It is a temporary state, a snapshot in geological time, for eventually the balance will tip and the sculpture will fall. So when you see the bishop standing sentinel or a rock that looks like a discarded tool, you are not looking at artifacts. You are witnessing the patient work of a planet-wide studio where the artists are the wind and time, and their medium is the very bedrock of Mars. These forms are a testament to a dynamic present, a world that is still being shaped grain by grain into new and bewildering shapes right before our robotic eyes. The wind sculpts the surface, but Mars guards its most vital resource just out of sight. Beneath the rust-colored dust of its mid-latitude plains, planetary scientists have uncovered a frozen ocean. Orbiting spacecraft like the Mars Reconnaissance Orbiter are equipped with radar instruments that can peer deep into the ground, and the data they have returned is staggering. They reveal sheets of nearly pure water ice, some as large as entire states, buried a mere meter or two beneath the surface. This is not a trace amount mixed with soil. This is a solid, gleaming reservoir, a second, hidden cryosphere waiting in the shallow subsurface. The most stunning visual proof comes from chance encounters. Fresh, small impact craters blasted into these plains by recent meteorite strikes act as natural core drills. In their ejecta and on their steep walls, orbital cameras have captured something brilliant, the unmistakable gleam of exposed ice. In enhanced color images, this material appears with a startling blue or white tint, a stark, clean contrast to the ubiquitous red dust. Within months, these bright patches fade, darkened by dust and sublimated away by the thin air, proving they were indeed volatile ice, not just pale rock. The existence of these shallow ice sheets is a revolution in our understanding of Mars. First, they are a climate time capsule. This ice is not at the poles but in temperate regions. Its presence there tells us that in a different climatic era, perhaps when the planet's tilt was more extreme, snow fell at these latitudes and accumulated into glaciers that were later buried and preserved. It is a direct record of a wetter, more dynamic climate cycle etched into the ground itself. But the importance is not just historical, it is profoundly practical. For any future human mission to Mars, water is the single most critical resource. It is life support, it is radiation shielding when incorporated into habitats, and when split into hydrogen and oxygen, it is rocket fuel. The discovery that vast quantities of this precious substance lie just a shovel's depth away in large parts of the planet transforms the entire equation of colonization. Instead of having to haul every drop from Earth or mine it laboriously from deep, mineral-bound sources, pioneers could literally go to a mapped deposit and dig. This accessible ice turns a forbidding desert into a potential oasis, making the dream of a sustained human presence not just possible but strategically feasible. These hidden sheets are the red planet's greatest kept secret, a frozen promise buried just beneath our feet. Hidden ice may fuel our future, but our minds are constantly fueled by the past, seeing familiar shapes in every alien corner. This tendency doesn't stop with faces or figures. It scales up to include entire landscapes. One of the most charming examples is a feature lovingly dubbed the Mars whale. In a vast, empty crater basin, a long, smooth, dark formation rises from the dust, with a rounded head and a tapered body that looks exactly like a colossal cetacean breaching a rust-colored sea. It's a perfect illusion of biology, yet it is simply a wind-sculpted mesa or dune field, a landform kilometers long. On a much smaller scale, another rover image once sparked the legend of the Mars rat, a tiny dark object perched on a rock that, with a little squinting, resembled a rodent with ears and a tail waiting for a crumb. Of course, it was just a curiously shaped pebble, likely no bigger than your fist. These are not isolated incidents. Spend an hour browsing the raw image galleries from Curiosity or Perseverance, and you'll start seeing things: a crab-like shadow, a thigh bone, a grinning skull. This game of cosmic pareidolia is a universal human experience, and it's incredibly fun. It speaks to the incredible pattern-matching software running in our heads, a survival tool honed over millennia to instantly recognize potential threats or resources in the dappled light of a forest. On Mars, with no forests to interpret, our brains apply the same urgent scrutiny to rocks and shadows, desperately trying to categorize the utterly unknown into the comforting bins of the known. The crucial lesson always is one of scale. Our eyes and brains have no built-in ruler for the Martian landscape. That whale is not animal-sized, it's city-sized. The rat is not a creature but a stone. The doorway we saw earlier is just a crack. When we forget the immense distances and dimensions involved, we shrink the planet to a backyard, making the extraordinary seem mundane and the mundane seem miraculous. So the next time you see a raw image from the surface, go ahead and play the game. What do you see in that jumble of stones? Share it, laugh about it. Then take a step back and remember the truth is often grander. That strange shape isn't a lost artifact, it's a mountain. And a mountain shaped by billions of years of alien geology is in the end a far more thrilling discovery. Our brains delight in seeing whales and rats, but Curiosity's instruments see something far more promising. As the rover drilled into the bedrock of Gale Crater, it uncovered a network of pale, glowing rings. These are the mysterious halos, light-colored bands that trace through the dark rock like ghostly veins, outlining ancient fractures in the stone. They are not just a visual oddity, they are a chemical fingerprint, and their composition is what makes them so compelling. Analysis revealed these halos are intensely rich in silica, the same mineral that makes up quartz and glass here on Earth. Their story begins with a crack, a fissure splitting the ancient Martian bedrock. Then imagine groundwater, not a raging river but a slow, persistent seep, filtering through that underground network. As this mineral-rich water moved, it acted as a subtle solvent, gently leaching silica out of the surrounding rock. Later, as conditions changed, perhaps as the water evaporated or its chemistry shifted, that dissolved silica precipitated back out. It crystallized directly within the fracture and the porous rock immediately around it, cementing the grains together into a new, much harder substance. This process left a permanent, pale tattoo around the crack, a halo of hardened material that resisted erosion long after the softer parent rock wore away. The significance of this cannot be overstated. On our own planet, silica is a champion preservative. In places like hot springs and geysers where silica-saturated waters flow, we find some of Earth's most exquisite and ancient microfossils. The mineral encases delicate cellular structures in a microscopic tomb of glass, protecting them from decay for billions of years. These Martian halos are evidence of an identical geological process. They tell us that not only was liquid water present underground in Gale Crater, but it was the exact kind of water with the right chemistry to perform this remarkable preservation trick. If ancient microbial life ever existed in that subsurface environment, if it clung to those damp rock walls or floated in those fluids, these silica-rich halos are precisely where we might find its fossilized remains. They are natural traps, having potentially captured and fossilized any biology that was present. This transforms them from curious geological features into one of the most high-priority targets in the entire search for life beyond Earth. They are not just rings in a rock, they are natural museums, and the exhibits they hold could be the most profound discovery in human history. Silica halos whisper of ancient preservation, but the Perseverance rover has captured a scene that looks like a magician's trick. Scattered across the ancient river delta of Jezero crater are rocks that appear to be floating. In several images, small, dark stones rest perfectly atop larger, lighter-colored boulders, as if carefully placed by an invisible hand. They defy the simple logic of gravity, looking less like geology and more like a carefully arranged art installation on an alien world. The explanation, however, is a beautiful demonstration of how planetary history is written in layers of strength and weakness. This surreal scene begins not with placement but with erosion. The story is written in the very composition of the stones. The smaller, darker rock perched on top is almost certainly a fragment of a much harder, more resistant layer that once capped the entire area. Think of it as a durable shell, a slab of volcanic basalt or heavily cemented sandstone. Beneath it lay a thicker stratum of much softer material, perhaps loosely compacted clay or silt deposited by the very river that once filled this crater. For eons, the relentless Martian wind has scoured this landscape. It attacks the softer material with far greater efficiency, sandblasting it away grain by grain. The hard cap rock, however, erodes at a glacial pace. As the softer pedestal is slowly eaten away from all sides, the durable cap above is left undercut and unsupported. Eventually, sections of this cap layer fracture and break off under their own stress. What we see as a floating rock is one of those surviving fragments. It hasn't moved upward, the world has simply fallen away beneath it. The larger, lighter rock it sits upon is not a separate entity, but the dwindling core of the original pedestal, still being sculpted by the wind. This process, creating what geologists call a pedestal rock or a ventilfact, is a slow moment balance between destruction and preservation. Each floating fragment is a timestamp, a clue to the sequence of events that built Jezero crater. It tells us that this river delta wasn't just a single wet event. It was a complex environment where different kinds of sediment, hard and soft, were laid down in a specific order. The fact that we see this phenomenon here, in the exact location scientists hoped would preserve signs of ancient life, is profoundly telling. That softer material being eroded away could be the very lakebed mud that might have trapped and preserved organic molecules. These seemingly impossible floating rocks are therefore more than a curiosity. They are active participants in the rover's mission. They guide the scientists, pointing to where the most interesting, ancient, and potentially life-bearing layers are being exposed by the patient wind, turning the entire delta into an open book, its pages slowly being turned by the Martian air. That surreal landscape of floating stones is shaped by vast, patient forces, but sometimes the most telling details are etched into a single rock. On its journey, curiosity once rolled up to a stone that stopped scientists in their tracks. Its surface was not smooth or randomly pitted, but covered in a perfect geometric grid of raised ridges, a pattern so precise it looked like a giant had pressed a waffle iron into the Martian bedrock. This was no manufactured artifact, but a stunning example of one of geology's most intricate artworks, a formation called boxwork. The story of this waffle rock begins deep underground in a fracture network. Mineral-rich fluids, likely sulfate-charged water, once seeped through a maze of tiny cracks within a larger mass of rock. As the water moved, it deposited its dissolved minerals along the walls of these fractures, slowly building up hard, resistant veins of material like plaster filling the seams in a wall. Then the environment changed, the water disappeared, and eons of erosion took over. The key is that the original host rock was softer, more susceptible to weathering than the hardened mineral veins now threading through it. The relentless Martian wind and dust began to scour the surface, stripping away the softer material grain by grain, but the gridwork of mineral veins, being much tougher, resisted. They remained standing as the rock around them vanished, leaving behind a delicate, raised latticework that now projects from the surface. This exquisite texture is far more than a curiosity. It is a fossilized map of an ancient plumbing system. Every intersecting line traces a path that fluid once traveled. The size and spacing of the grid tell us about the pressure and flow of those long-vanished waters. The mineral composition of the veins themselves, often sulfates, reveals the chemistry of that fluid, hinting at whether it was acidic, salty, or potentially even habitable. So while it may look like a cosmic breakfast left behind, this waffle rock is actually a meticulous chemical ledger, a permanent record of the dynamic, wet, and interactive processes that once thrived beneath the cold, dry surface we see today. The waffle rock's intricate grid maps an ancient underground flow, but on the surface, entire landscapes speak of movement on a grand scale. Some of the most common yet strangely uniform sights on Mars are the vast, gravel-strewn plains. From orbit, they look like endless parking lots paved with small, rounded stones, stretching to the horizon with a monotonous perfection that feels almost unnatural. These are not the jumbled, chaotic rock fields you might find at the base of a mountain on Earth. Instead, they are vast sheets of similarly sized pebbles, often remarkably smooth and rounded, as if tumbled in a giant's polishing machine for eons. That feeling is the key to their origin. This uniformity and smoothness are classic fingerprints of water, not wind. Wind-blown sand tends to be angular and sharp, scoured into facets. But water, flowing in rivers or shallow streams, rolls stones against each other. Over vast distances and immense stretches of time, this constant abrasion rounds the edges and grinds rocks down to a common size, sorting them by weight and shape. These Martian gravel fields are therefore not random debris. They are the smoothed, sorted remnants of ancient riverbeds or floodplains. They tell us of a time when water wasn't just a seep or a groundwater trickle, but a powerful, persistent surface force that could shape entire regions, carrying and grading stones across hundreds of miles. They are the dried-out bones of vanished rivers, a stark and powerful testament to a planet that once knew the persistent, shaping flow of liquid across its face. Yet, right beside these watery relics, you often find another contradictory feature. Winding across the same plains, sometimes even superimposed over the gravel, are enormous, sinuous ridges. They look like giant sand dunes, but frozen in mid-motion, with graceful, sweeping curves that can be several stories high and hundreds of feet from crest to crest. These are megaripples, and they are formed by wind. On Earth, we have small versions of these in sandy deserts, but our atmosphere is thick enough to regularly reshape them, keeping them active and mobile. On Mars, these features are colossal, and they are utterly still. They are monuments to a paradox. Their very existence proves the wind was once strong enough, and the atmosphere likely denser to move the vast amounts of sand needed to build such immense structures. But today, Mars's air is too thin. The wind whispers, but it no longer has the strength to push these gigantic waves of sand. They are stranded, frozen in elegant forms that might be millions of years old, relics of a more dynamic atmospheric past. So in a single frame, you can see two histories written side by side, the rounded gravel that speaks of persistent, flowing water, and the fossilized megaripples that whisper of powerful, ancient winds. This juxtaposition is the heart of the Martian mystery, a world that once thrummed with both fluid movement and atmospheric force, now silent, leaving only its beautifully preserved footprints in the stone and sand for us to decipher. A stark, pale ribbon cuts across the rust-red landscape at the base of the Jezero Delta. This is the feature NASA scientists have named Bright Angel, a striking exposure of light-toned rock that the Perseverance rover is now intently studying. After traversing the ancient river fan, the rover's arrival at this bright outcrop marks a deliberate plunge into deeper time. While the delta sediments tell the story of the lake itself, these pale rocks likely represent something even more fundamental, the ancient basement upon which that lake was built. Their light color is the first clue, often indicating a different mineralogy than the iron-rich, oxidized sediments that give Mars its red hue. These could be older sedimentary layers deposited before the lake filled, or perhaps even volcanic ash layers or chemically altered bedrock. The prevailing and most exciting hypothesis is that Bright Angel represents a unit shaped by groundwater. Long before the crater held a lake, and even after it dried up, groundwater could have percolated through this deep rock for eons. Where groundwater interacts with rock, it leaves a chemical signature, altering minerals and depositing new ones in cracks and pores. On Earth, such groundwater environments are often teeming with microbial life protected from harsh surface conditions. If Mars ever developed life, these subsurface water-rich niches would have been prime real estate. By drilling into Bright Angel, Perseverance isn't just sampling another rock, it is attempting to reach back to the earliest chapter of Jazero's habitable history, a time when persistent groundwater may have created a stable, potentially life-friendly environment deep within the crater floor. The samples it collects here could therefore be the most primitive and revealing of the entire mission, capturing a snapshot of Mars not from its surface waters, but from its hidden, subterranean whispers. While Bright Angel may hold clues to ancient groundwater, other Martian landscapes suggest that water and mud might still be forcing their way to the surface today. Orbiting cameras have mapped vast regions of what scientists call pitted terrain, strange fields of circular, shallow depressions that dot the plains like the dimples on a golf ball. These are not impact craters, they lack the raised rims and ejected debris. Instead, they look like something has collapsed or erupted from below, leaving behind these neat, often clustered hollows. One compelling and tantalizing hypothesis is that we are looking at the footprints of mud volcanoes. On Earth, mud volcanoes form when water-saturated sediment, buried deep under pressure, finds a weakness in the overlying rock. This slurry of mud, water, and gases forces its way upward, erupting onto the surface as a cold, slow-moving ooze that builds up a conical mound, often with a central vent or pit. Mars could be experiencing a similar process, but in a frozen, slow-motion state. Imagine a deep aquifer, a layer of water-rich mud or clay sealed beneath a kilometer of frozen ground. Changes in temperature or tectonic stress could increase the pressure in that layer until it finally finds a crack. The mud, kept fluid by dissolved salts that act as antifreeze, then squeezes upward, erupting onto the frigid surface. There, the water would instantly flash freeze or boil away in the thin air, while the fine sediment spreads out, leaving behind a characteristic low mound and a collapsed pit. The implications of this are staggering. First, these features would be direct conduits, bringing material from tens or even hundreds of meters below up to the surface where our rovers could sample it. It would be like a natural drill core, delivering a taste of Mars's deep, potentially habitable subsurface without us having to dig an inch. Second, and even more critically, such a process could solve the methane mystery. That deep, wet, geologically active environment is exactly where methane could be produced by subsurface chemistry, or even by microbial life. The erupting mud would act as a pipeline, transporting that gas from its deep source and releasing it directly into the atmosphere in localized plumes, exactly the kind of sporadic spikes that Curiosity has detected. So these unassuming pits are not just odd dimples, they could be the very vents through which Mars breathes. They are potential windows into a hidden, wet, and chemically active world, and possibly the long-sought source of the gas that keeps the dream of Martian life alive. Mud volcanoes might hint at a churning subsurface, but on the surface itself, Mars has developed a wrinkled, organic appearance that looks almost like living tissue. In the planet's mid-latitude belts, where orbital maps show abundant subsurface ice, the ground is often etched with a bizarre texture officially termed brain terrain. It is a landscape of convoluted, looping ridges and troughs, a labyrinth of rounded, squiggly lines that looks exactly like the surface of a human brain, frozen and magnified across miles of alien ground. This is not a trick of pareidolia, it is a real, widespread geological pattern, and its cause is a direct fingerprint of the ice hiding just below. The process begins with the intense cold. The soil in these regions is not just dusty, it is ice-cemented, a frozen mixture known as permafrost. As temperatures plunge during the Martian winter, this ice-rich ground contracts, cracking under the stress. It doesn't crack randomly, though. The contraction creates a network of fractures that naturally organize into polygons, much like the mud cracks in a dried-up puddle, but on a vast subsurface scale. This creates the initial blueprint, a geometric grid of potential ridges. Then comes the transformative power of sublimation. In the slightly warmer periods, the water ice locked in the soil doesn't melt, it turns directly into vapor. This sublimation happens unevenly. The ice in the center of each polygonal cell sublimates away more readily, causing the ground there to sink slightly. Meanwhile, the icy material along the initial fracture lines is more protected, or perhaps even receives a tiny influx of water vapor that refreezes, making it slightly more resistant. Over thousands of seasonal cycles, this slow, differential loss of ice exaggerates the pattern. The polygonal troughs deepen and widen, while the intervening ridges become more pronounced and, crucially, their sharp, angular cracks are softened. The relentless, grain-by-grain work of wind and sublimation rounds the edges, transforming a stark geometric grid into those signature, meandering, brain-like lobes. This terrain is therefore a frozen record of recent climate activity. It tells us that ground ice isn't just passively buried, it is an active participant in shaping the landscape, heaving, cracking, and vanishing in a slow dance driven by the Martian seasons. The very presence of well-developed brain terrain is a billboard announcing ice was here and not long ago. It signifies that the processes creating it have been at work in the geologically recent past, perhaps within the last few million years, suggesting that Mars's icy heart still beats, subtly reshaping its face with every passing orbit around the Sun. Brain terrain shows the subtle work of water ice, but at the planet's southern pole, the ice itself is vanishing in a pattern of startling perfection. The South Polar Residual Cap, a permanent fixture of frozen carbon dioxide, is not a smooth, white sheet. From high orbit, it resembles a colossal block of Swiss cheese, pockmarked by thousands of round, flat-floored depressions with steep, dark walls. These aren't impact craters, they are windows into an active, modern climate cycle. Each pit is a direct result of sublimation, the process where solid carbon dioxide ice turns directly into gas under the weak Martian sun. During the southern summer, sunlight preferentially warms the darker dust particles trapped within the ice. This absorbed heat triggers the CO2 beneath to sublimate, starting a small hole. Once begun, the process accelerates because the steep walls of the pit absorb more sunlight than the flat, reflective surface around it. This creates a feedback loop. The pit deepens and widens, its walls retreating year after year in a perfectly geometric dance. By comparing images taken over multiple Martian years, scientists have made a remarkable observation. These cheese holes are measurably expanding. The entire landscape is slowly, steadily evolving before our eyes. This makes the Swiss cheese terrain one of the most valuable climate monitors on Mars. The rate of change in these pits is a direct gauge of current atmospheric conditions, temperature, and solar energy. By tracking their growth, researchers can build precise models of the Martian climate system today, understanding how the planet responds to subtle shifts in its orbit and tilt. It is a stark and beautiful reminder that Mars is not a frozen fossil, but a dynamic world with seasons that literally sculpt its surface, one sublimating molecule at a time. But even the patient sublimation of the polar ice is just one part of a dynamic and beautiful atmospheric ballet. High above those Swiss cheese plains, the Martian sky itself comes alive with formations both hauntingly familiar and utterly alien. Our rovers have looked up to see delicate, wispy cirrus clouds drifting in the thin air, while orbiters have mapped colossal cloud systems that dwarf anything on Earth. Some of the most striking are the noctilucent or night shining clouds. These are high-altitude clouds of water ice crystals that remain illuminated by the sun long after the surface below has fallen into darkness, creating an eerie, glowing canopy against the blackness of space. They are a ghostly reminder that water vapor, though scarce, is still cycling through the Martian atmosphere. Then there are the giants, the orographic clouds that form as air is pushed up and over massive topography. Nothing demonstrates this better than the Lee wave clouds that stream from the summit of Arsia Mons, one of the planet's great shield volcanoes. For part of each Martian year, a remarkably stable, repeating cloud forms downwind of the volcano's peak. It can stretch for over 1,000 miles, a long, white filament of water ice that appears in the morning, grows through the day, and then vanishes, only to repeat the entire performance like clockwork the next day. This isn't just a pretty spectacle, it is a precise atmospheric instrument. The cloud's consistency tells scientists about wind speeds, atmospheric stability, and the humidity at that exact altitude. But Martian clouds aren't always made of water. During the cold polar winters, the atmosphere grows so frigid that carbon dioxide itself can freeze, forming clouds of CO2 ice crystals. These dry ice clouds play a crucial role in the planet's seasonal cycles as they snowfall and contribute to the growth of the polar caps. Studying this entire menagerie of clouds is like reading the vital signs of a global system. Each type reveals a different piece of the puzzle: the movement of water, the transfer of heat, the patterns of global winds on a planet with no oceans and dramatic temperature swings. By learning how clouds form and behave in an atmosphere only 1% as thick as our own, we are not just understanding Mars, we are stress-testing our fundamental models of planetary climate. It shows us how a world can still breathe, change, and express a fragile beauty even when its surface appears silent and still. High above the polar ice, the Martian atmosphere weaves its own delicate tapestry, but down on the steep slopes of crater walls and valley sides, the planet's skin is pocked with a more cryptic pattern. These are the hollows, strange shallow depressions that dot inclines across the mid-latitudes, often appearing in eerie, organized rows like dimples pressed into the rusty hillside by some giant, careful hand. They are not impact craters, nor are they the deep pits of possible mud volcanoes. They are subtle, almost shy features, typically just a few meters across and only a meter or so deep, yet their very presence and precise arrangement whisper of active, hidden forces at work just beneath our view. One compelling theory points directly to a hidden layer of purity, shallow reservoirs of water ice. Imagine a lens of nearly pure ice, a frozen pocket sandwiched between layers of soil, buried perhaps just half a meter below a steep slope. When this slope faces the sun, the weak Martian warmth penetrates the thin overburden. The ice does not melt, it sublimates, turning directly from solid to gas. As that supportive ice vanishes into the thin air, the soil above loses its foundation. The surface becomes a fragile ceiling over an empty cavity. With nothing left to hold it up, that ceiling collapses inward in a gentle, contained slump, creating one of these neat, rounded hollows. If multiple ice lenses lie along the same layer within the slope, their sequential collapse could easily explain the hollows appearing in those distinct marching rows. It is a quiet process of theft where the ground simply falls into the space left behind by escaping vapor. Yet another hypothesis connects these hollows to the same enigmatic forces behind the recurring slope lineae, the dark streaks. In this dry model, there is no ice at all. Instead, these depressions could be the starting points or aftermath of dry granular flows. A small section of loose, dusty material on a steep slope might become unstable, perhaps triggered by the sublimation of seasonal carbon dioxide frost. As this patch gives way and slides downslope, it could scoop out a shallow scar, a hollow, at its point of origin. Repeated slides along the same weak layer could then generate that same linear pattern. The debate between these wet and dry origins is more than academic. It strikes at the same core question raised by the dark streaks: how active and aqueous is the modern Martian surface? Are these hollows proof that clean, accessible water ice lies tantalizingly close to the surface on sun-facing slopes, a potential resource marked by its own collapse? Or are they simply another expression of Mars's dry, mechanical geology, where dust and sand are the only moving parts? For now, the hollows keep their secret, each neat dimple a small question mark etched into the hillside, a reminder that even the most unassuming features can be gateways to understanding the hidden dynamics of a world that is still, in its own subtle way, very much alive. The hollows are subtle scars of hidden processes, but on the floor of Jezero crater, the Perseverance rover has encountered debris of a very different kind. Littered across the rust-colored sand are objects of startling artificiality, jagged pieces of shiny metallic fabric, a tangled web of high-strength cords, and a shattered, curved shell that looks like a giant broken egg. These are not geological formations, nor are they relics of some lost civilization. They are pieces of Perseverance itself, or more accurately, the discarded hardware that delivered it safely to Mars. When the rover's cameras turned to photograph these scattered remains of its own heat shield, parachute, and backshell, the images created a profound and surreal moment. Here was humanity's own footprint, gleaming and alien against the ancient dust. The parachute, a technological marvel of nylon and Kevlar, lies crumpled like a discarded jellyfish, its brilliant white and orange stripes a violent splash of color in a monochrome world. The heat shield, a scorched and fractured disk of advanced composite materials, rests where it impacted at hundreds of miles per hour, its inner structure exposed like the ribs of a mechanical beast. These objects cause a cognitive double-take because they are so utterly, unmistakably out of place. They are the antithesis of everything we have been searching for, not ancient and natural, but modern and manufactured. They represent a meta-mystery, one where the detective finds its own discarded tools at the scene of the crime. This debris field is far more than just litter. It is a timestamp and a turning point. It marks the precise moment, February 18, 2021, when human engineering became a permanent part of the Martian geological record. These artifacts will not erode like a sandstone hoodoo or vanish like a seasonal cloud. They are made of materials designed to withstand extremes, and in the gentle, slow environment of Mars, they may persist for millions of years, becoming future fossils of our first tentative reach across the void. This scattering of our own technology forces a moment of reflection. For decades, we have scoured this world for any sign that we are not alone, for any artifact that says someone else was here. Now, we are the ones leaving the artifacts. Every rover wheel track, every drill hole, every discarded lens cap, and now this grand debris field is an indelible mark of our presence. We have transitioned from pure observers to active participants, and our machines are the first settlers. These shiny fragments are a promise and a responsibility. They are the blueprint of our ambition, proof that we can land complex, delicate laboratories on another world. But they also ask a quiet question of us as we plan for more complex missions and perhaps one day human footsteps. What kind of legacy will we choose to leave on this pristine desert world? Will our marks be only the scattered shells of our arrival, or will they become the foundations of something new? The final strange thing found on Mars is, in the end, us, or at least the brilliant, fragile pieces of ourselves we have already sent ahead. From our own scattered spacecraft debris to colossal atmospheric plumes, the sheer diversity of strange things found on Mars is nothing short of breathtaking. We have wandered through a gallery of illusions where our minds see faces, figures, and doorways in wind-carved stone. We have witnessed the patient artistry of erosion, crafting floating spoons, chess-piece bishops, and delicate mineral flowers from bedrock. We have uncovered profound, tangible evidence of a lost world, from iron blueberries that prove ancient groundwater to polygonal dragon scales mapping buried ice. And we have been humbled by fleeting, colossal mysteries, from seasonal methane whispers and crawling polar spiders to towering plumes that defy explanation. This journey reveals a fundamental truth: Mars is not a static, dead rock adrift in space. It is a world of active, dynamic processes. Its thin atmosphere weeps clouds and carves landscapes. Its subsurface ice heaves and cracks the ground into brain terrain, and its poles sublimate into Swiss cheese before our orbiting cameras. For every mystery that sparks wild speculation, science has provided a natural explanation more wondrous than fiction, uncovering the epic forces of wind, water, chemistry, and time that shape this alien environment. Yet a few profound puzzles, like the source of that enigmatic methane, remain tantalizingly unresolved, keeping the door firmly open to the possibility of astounding, even biological, discoveries in the decades to come. Each strange formation, from the smallest concretion to the largest plume, is a piece of the grandest puzzle, the story of a neighboring world with a complex, dramatic, and surprisingly active history. Which of these 30 Martian mysteries captured your imagination the most? Was it the haunting ghost dunes, the potential mud volcanoes, or the shimmering fields of impact glass? Let us know in the comments below, and if you enjoyed this deep dive into the Red Planet's secrets, be sure to subscribe for more explorations into the greatest mysteries of our cosmos.